Good evening, everyone, or whatever time it is where you're joining from. I'm Bridger Herman, pronouns he, him, his. Today, I'd like to discuss multi-touch querying on data physicalizations in immersive AR, which is a novel approach to hybrid virtual plus physical visualization. Let me begin with an introduction to physicalization itself and why it's important. One of the key ideas behind physicalization is to leverage our human perceptual abilities that go beyond the visual and into the tactile. It even allows us to depict more data than traditional digital visualization by using physical material properties of these physical objects. Physicalizations engage our senses and make huge steps toward making our data approachable, such as putting our data in a museum or allowing individuals to participate by placing physical tokens. But what if the user wishes to make dynamic queries into their data to select, filter, sort, rearrange, or otherwise interactively explore their data? Augmenting physicalizations with digital content is one solution to this interactivity challenge. These so-called hybrid visualizations combine physical and digital elements into one cohesive, interactive visualization. Prior work in this area indicates two primary challenges and requirements for these hybrid virtual plus physical systems. First, we've got to be able to sense input from the physical world, such as interactions like pinch to zoom, touch to select, and swipe to pan. For this, we need a high accuracy method to pick up a user's touch on an irregular physical surface and translate it into digital space, and then react to it with our digital content. Also, when we move a physical object, we should be able to have the related virtual object follow directly with any translation and rotation. For this alignment and registration of virtual and physical spaces, we need to have a high accuracy and low latency pipeline for tracking. So we're not the first ones to encounter these particular challenges. On the left, we have tangible landscape and tangible cityscape, which are projection-based physicalizations that use a depth camera for touch input and only require an initial alignment between virtual and physical space. Tangible cityscapes also qualifies as an active physicalization, which is a shape-changing display where the columns actually move up and down according to the data. This example shows a window-based AR physicalization of a molecule using a video camera and image markers to continuously register the virtual and physical world together. And Planwell also uses continuous image-based tracking, and it uses a pen input device to make selections on an immersive AR visualization. Our approach to these problems uses touch through the physicalization and registers the virtual and physical components using image targets affixed to an optimized tracking base. For the remainder of this talk, we'll go into detail on our approach for addressing these requirements, and we'll demonstrate the approach as applied to exploratory visualization techniques and share a couple of evaluations. To solve the registration challenge, we use the Vuforia image tracking system and a custom truncated pyramid base. So here we see 4 image targets that are tracked, shown by their axes in red, green, and blue. The truncated pyramid design was informed by initial latency trials of oscillating image targets. And through these trials, we determined that the latency increases for each added visible target. So on the final tracking base, we try to make sure that there are only 1 or 2 images visible during normal operation of the system. To address the other challenge of touch sensing, we introduce touch through the physicalization. We start with our original data, and in this example, it's volumetric 3D time-varying data from supercomputer simulations and remote sensing. This portion of the data in particular includes ice, water, and terrain from the Filchner-Ronne ice shelf in the Antarctic, and contains variables like temperature, velocity of the currents, and salinity. After this, we transform the data and split it into tiles. We experimented with different tile shapes and sizes, but for example, one of our first iterations was these 2 centimeter by 2 centimeter squares. But ultimately, we arrived at the design for these 1.5 centimeter diameter hexagons, which are then placed into our physicalization, our final physicalization here. Once the physicalization is tiled and split, then we go ahead and print it. These columns are sliced in such a way that a regular FDM printer using PLA filament can print them. And indeed, that is what we did in our case. So once this is all said and done, we place the whole physicalization on top of a force sensing tablet, say a Sensel Morph, and we are then able to react to a user's touch on the physicalization in the AR visualization. So putting it all together, we have the tracking base, which determines the registration between AR visualization and the physical world. We have the tiled physicalization that's placed on top of a pressure sensing tablet. And combined, these two will sense the user's touch. That gets sent to the AR device so that the AR visualization can react to the user's touch. So now that we have a basis for this technical approach, let's apply it to some of the most common data exploration techniques used for 3D spatial data. For the first technique, we define a cutting plane into volumetric data as a user's 2 touch points and the up vector pointing out of the physicalization. In practice, the user can touch 2 points and a white preview plane appears. Once the user releases their fingers, then the actual query is made into the data. And if the user wants to adjust the plane, they can simply move their fingers around until they're happy with the location of the plane. And then the query is made. We also implemented a stream rake for analyzing vector fields. The stream rake takes a user's touch point and the up vector and seeds streamlines along this vertical line and then advects those streamlines. In practice, the user can also touch points on the physicalization to seed streamlines. So we can have like a white preview stick sort of thing that shows the streamline rake. And if the user wants to pick different location for the streamlines, they just need to move their finger. To partially overcome the limitations of this small model, we've also implemented physicalization as a world in miniature. And this not only allows for multi-scale views of the data, but also allows the user to have the physicalization as a haptic proxy for the larger AR visualization. It's also important to note that the physicalization correctly occludes the virtual visualization. So notice how the cutting plane disappears behind the peak and then reappears on the other side, on the right side of this physicalization here. So what about the evaluation? We compared a user touch accuracy with and without the tiled physicalization present. After informed consent, we asked each of our 8 participants to touch a sequence of 30 projected dots on the physicalization and on the bare force sensing tablet. We found that the Euclidean distance from the ground truth points for both of these conditions was just over 3 millimeters, and a Wilcoxon-signed rake test was unable to find a significant difference between these conditions. So the difference in the error between these conditions is subtle enough that we would need a much larger sample size to detect a significant difference here. We also asked a climate scientist studying ocean currents underneath Antarctica's ice sheets to use our system. As I was using it, he remarked that the physical bathymetry, the 3D print really grounded him in his usage of the AR visualization. And he also thought that it would be super useful to have a system like this when collaborating with other scientists so that they would have a physical reference frame to communicate by. He also had some suggestions for us, such as the small scale of the physical printout was a little bit limiting, and having it in a much larger form, even if it's a little lower resolution, would be much more useful. He also mentioned that it might be useful to have even more data depicted on the physical model itself. So such as having the grounding line where the terrain, the water, and the ice meet would be super useful to have on the physicalization. So despite positive results from both of these preliminary evaluations, there are still some limitations to our approach. Firstly, the force sensing tablet is only 24 centimeters by 13.8 centimeters, which limits the touch area, the touch sensing area that we're able to have, and therefore the print size. The print time might also be prohibitive in some workflows. So the Antarctic print that we've been using as examples in this talk took about 2 days to print at a layer height of 0.15 millimeters, which is pretty high resolution. So there are some trade-offs there. But touch through the physicalization also works best for convex geometries that can be adapted to have a flat bottom, which doesn't necessarily apply to every geometry. It works really well with, say, terrain data sets, but if you have a sphere, you may need to adapt your data in a special way to make it work with this particular touch sensing mechanism. During the scientist interview, the physicalization was used both as a querying mechanism and as a contextual piece. So this brings questions like, what is the role of physicalization in this hybrid context? And how much data do we encode in the physical world versus how much do we leave in the digital visualization? Our approach also has implications for adapting new querying techniques that use pressure or even the tactile context of the data, such as if you've pressed in a valley or on a peak, or even within a particular subvolume. In summary, we set out with this lofty goal of fusing the interactive querying, animation, and data exploration of digital visualizations with the immediate and relatable tangibility of physicalizations. But even with modern input technologies and immersive displays, combining these things is still a hard problem. Through our process, we found that the approach of touch through physicalizations is viable as an input mechanism for hybrid visualizations. But we also need to design for the future of hybrid virtual and physical visualization, including adapting current visualization software to a tangible context and continuing to develop hybrid visualizations that lead to greater clarity and communication of our data. I'd like to just acknowledge my co-authors, in particular Max Omdahl. Shout out to him, super instrumental in getting this thing off the ground. And I'd like to thank the National Science Foundation for funding and the E3SM project for data. And thank you all for attending my talk. Any questions?